History of Vector Analysis, Episode 21, Formalizing Vector Notation. You are here. Hey, it's old Doc Goler. Welcome back. I've spent the last several episodes going through the content of the Gibbs Heaviside vector analysis, specifically the different definitions and multiplication rules of the IJK unit vectors, the arithmetic, algebraic properties such as A cross B cross C is not associative, but it does follow the back-cab rule, how the divergence and curl operators function, content. Okay, form and content. Many of us physicist types like to think of ourselves as being more interested in the deep, meaningful content rather than the shallow surface level form. But the fact is that form is also important, perhaps even equally as important. The difference between Roman numerals and Arabic numerals is largely one of form, but try doing division, or calculus with Roman numerals. All right, so the subject of this episode is the formalizing vector notation. To briefly summarize the formalisms of vector notation thus far, Hamilton coined the terms vector and scalar prior to 1853, but this was the year that his lectures on quaternions appeared. He defined a subset of quaternions, here showed as capital Q, that were the 4D products of two 3-parameter zero real quaternions. Hamilton did not formally have a dot product or a cross product, which were specifically defined for 3D vectors. Okay, but he did have what he called the scalar part of Q and the vector part of Q formalized thusly, which were their forerunners. He also defined a version of the del operator, but he did not apply it to his quaternions. Then we had Tate, who published the first edition of his elementary treatise in 1867. He used lowercase Greek letters to represent quaternions and defined scalar and vector parts the same way that Hamilton did. But he did go further, and he applied the del operator to these quaternions, thus defining the precursors to the divergence and curl. Sometimes he used periods to separate the operations, sometimes he didn't. Maxwell published his treatise on electricity and magnetism in 1873. I need to reiterate that Maxwell wrote his book in two mathematical formats, quaternions, as shown here, and Cartesian components, which are not. Maxwell needed Greek letters for other purposes, so he used German script letters instead. His focus was on 3D vector quantities, the electric field, displacement field, magnetic field, etc. As a result, when he wanted to express the products of two of these still technically 4D quaternions, he would express the equivalent of the dot product and the cross product like this. Notice that Maxwell used individual letters in defining his quaternion / vector, here F, G, and H, to represent the magnitudes along the X, Y, and Z axes. Since his treatise discussed multiple vector quantities, this notation had the drawback of running through symbols pretty quickly. Then came Gibbs. In earlier episodes, I discussed some of the important content of his 1881 pamphlet, defining a 3D system rather than a 4D one, redefining IJK to be real rather than imaginary, and developing two different sets of product rules for those IJKs. But he made some critical contributions to the formalisms of vector analysis as well. I do not have a hard copy of this pamphlet, by the way, but it is available for free on the internet as a PDF. There is no physics in it, only math. Okay. The entire second half, by the way, is on linear vector fundamentals, or dyadics, a form of what we call today tensors. It's actually a nice piece of work. Perhaps the most visual contribution of Gibbs notation is the introduction of the cross symbol to represent the vector product. You can see it here in multiple places on the box on the left. This change is more than a simple substitution of A cross B for VAB. VAB indicates taking part of a larger multiplication product. A cross B, or what Gibbs called the skew product, indicates a standalone operation, one that is distinct from multiplication and also from the dot product, or what he called the direct product. Note that in the case of the dot product, this dot here is now represents an active operation rather than a passive separator. Gibbs also introduced the lower dot and cross symbols for what he called the divergence and curl operations following Maxwell's terminology. Here is a summary of Gibbs' contribution to vector formalism. He avoids Maxwell's German script letters, returning to Tate's lowercase Greek letters, but I emphasize that Gibbs' vector does differ fundamentally from Tate's and Maxwell's. Gibbs's object is a 3D object with real IJKs, not a 4D object with imaginary IJKs. I write the IJKs here in black rather than in color to indicate this. The dot product and the cross product look pretty close to what we use today, except that the dot is along the bottom rather than centered. The same holds true for the divergence and the curl. Then there is Oliver Heaviside. His changes to the content of vector analysis were almost identical to those of Gibbs and were performed completely independently, according to historian Michael J. Crow. He published several papers on his version of vector analysis between 1883 and 1885, but here I will credit the date of his contributions to 1893, the date he published his book Electromagnetic Theory. Here is my copy of this important book. There are a few points I want to make about it before we come back to the task at hand, which is vector formalism. First, a comment on his style, which was remarkable, especially considering the era. From Michael J. Crow's history, quote, Heaviside's writing style can be placed somewhere between brilliant and obnoxious, depending on one's point of view. At least he was never dull. Indeed, G.M. Minchin referred to a Heaviside as the Walt Whitman of English physics. And like that so-called poet, he is certain to raise aversion to his peculiarities. Next, besides being readable and even entertaining, if you enjoy his witty sarcasm, it is a mere 466 pages long, which is less than half the length of Maxwell's 2-volume treatise that was published 20 years earlier. This is important because, unlike Gibbs' pamphlet, Heaviside's book includes physics. It essentially covers all of the material in Maxwell's treatise in a concise and compact form. In fact, Heaviside's book eventually became the standard textbook for Maxwell's electromagnetic theory and remained so for many years. It was much more accessible to students than Maxwell's treatise, as well as to working physicists and engineers. Just as important for our story of the history of vector analysis is that a full third of this book, 173 pages, was a long chapter entitled The Elements of Vectorial Algebra and Analysis. So this book was self-contained. It taught vector math along with electromagnetic theory. People turned to Heaviside to learn Maxwell's theory, and in the process picked up Heaviside's vector analysis. To get one, you pass through the other. Let me take a step back here. Unlike Gibbs, Heaviside rewrote Maxwell's entire theory in 3D vectorial form. Okay? Perhaps translated might actually be a better word. But he did more than that. Okay? He did some physics as well. One of the things that he did was to rewrite the dozen-plus formulas that we today call Maxwell's equations into a mere 4. Okay? He didn't put them all together. His divergence equations appear on page 50, while the curl equations appear more than 300 pages later. But the fact remains that it was, in fact, Oliver Heaviside who first published Maxwell's equations in their more or less current form. So spare a thought for Oliver Heaviside the next time you see this t-shirt. But let's return to our discussion of Heaviside's contribution to the current form of vector analysis. Like Gibbs, Heaviside rejected Maxwell's use of the German script letters on the grounds that they were too difficult to read and write, and that most printers didn't carry them. Unlike Gibbs, however, he replaced his vectors with Roman letters, both uppercase and lowercase. But Heaviside's biggest practical contribution to the formalism was to express the 3 components of each vector as a single letter with subscripts. He did this specifically to reduce the number of letters that each type of vector field would require from 3, as over here in Maxwell, down to 1. To make it clear when he was talking about the 3D vector rather than the 1D components, he proposed to use the Clarendon typeface, what we today call bold, for the vector and the regular unbold for the components. Since IJK were unit vectors, he expressed all of these in boldface. He explicitly noted the practical advantage that all printers had Clarington/bold typeface on hand. Simple but brilliant. There were some objections to this. Typesetters may have no problem with constructing letters in bold, but humans often do. I don't know who it was who invented the arrow over the letter format that you probably use when you turn in your E&M homework, but it wasn't Heaviside. So now let's post Heaviside's contribution to the format of vector analysis. Here it is, the bold Roman letter for the vector comprised of 3 subscripted but unbolded components. I think Maxwell would have approved. Being unaware of Gibbs' work, Heaviside did not use the dot or the cross symbols. Instead, he wrote the scalar product of 2 vectors as AB, not SAB, just AB, but the vector product as VAB. He did the same for the divergence and curl, although as I showed a bit earlier, he also used the letters DIV for divergence and the word curl to express these operations. These forms still appear today from time to time. It would be easy to assume that when Heaviside's book came out that vectors just took over E&M. This was not the case. Neither Gibbs nor Heaviside were well known at the time, and when Heaviside's book was published, there were about 30 books on quaternions. Likewise, not only was the aging Lord Kelvin still opposed to all of those silly multiple algebra techniques, so were other senior academic figures such as Arthur Cayley. Chapter 6 of A History of Vector Analysis is entitled A Struggle for Existence in the 1890s. In this chapter, Crow reviews many of the published articles in a multi-year debate over the competing mathematical methodologies to model Maxwell's theory. This included articles and letters to the editor by Tate, Gibbs, Heaviside, Cayley, and others in major, widely read journals such as Nature, Philosophical Magazine, and Science. This debate not only entertained a large number of professionals over an extended period, it made them aware that the Gibbs-Heaviside vectorial approach, whether you liked it or not, existed. It also brought quite a bit of professional fame to Gibbs and Heaviside personally. Acceptance of the Gibbs-Heaviside approach in nomenclature grew slowly but steadily, and more new professional articles and books chose to employ its techniques in their analyses. Yet, there were significant differences between the Gibbs formalism and the Heaviside formalism. There was not yet an official canonical version of vector analysis. Enter Edwin Bidwell Wilson. Gibbs never did write a published book on vector analysis. He did, however, give such an assignment to a former student and now young colleague of his, a man named Edwin Wilson. Crow states that Gibbs took the hands-off approach to Wilson's efforts, ostensibly on the grounds that he was busy writing what would essentially become the first book on statistical mechanics, microstates, macrostates, and all that stuff. Okay, Wilson published Vector Analysis, a textbook for the use of students of mathematics and physics in the year 1901. Like Gibbs' pamphlet, it was a math book. It contained little in the way of physics. It used Gibbs' notation for the dot product and the cross product and all of Gibbs' vector identities. However, it also incorporated Heaviside's approach for expressing the vectors and their components. It was also Wilson in this book who first centered the dot in the dot product and in the divergence. Wilson also coined the word del as the way to pronounce the symbol formerly known as nabla. This book received favorable reviews, and it was popular enough to have a second edition in 1909. Wilson's book standardized or canonized vector analysis into the form we know it today. However, according to Crow, it still took another 10 years or so, till about 1910, to get to the point where the Gibbs-Heaviside-Wilson vector approach to Maxwell's E&M completely replaced the quaternion and Cartesian component approaches. Okay, to summarize, Crow argues that the acceptance of vector analysis was driven by the physics and engineering community's needs to understand Maxwell, which they did through Heaviside's shorter and more readable book, and from there, Gibbs's contribution, both form and content, via Wilson's textbook. So that's it. We have our happy ending. Happy if you love vector analysis anyway. The math was formalized in 1901, and a decade later it had taken over as the way to do electricity and magnetism. It also came into use in many other branches of physics and engineering, such as fluid mechanics. I note in passing that tensor analysis also evolved from these same sources at the same time, just in time for Einstein's general relativity, which appeared in 1916. Okay, so that's it for the history of vector analysis. I'll be back with one more episode to sum everything up and to express a few closing thoughts. See you then, I hope.